Hello world! Let's investigate which personal informations can be inferred from your smartphone sensors. The dataset we will be using contains the sensor data for 6 different activities for each of 30 study participants. In the next few minutes, I'll explain where the data I used came from and how it has been recorded. Then we will dive right into the data and explore some basic characteristics of it. Afterwards, we will build a small machine learning pipeline to infer the user's activity from the sensor data. Thereafter, we will try to deduce the user holding the smartphone in the same way. And finally, we will attempt to get some insights for the personal walking style of each participant. Of course, you can find the code on Kaggle and Github to recreate everything. Let's start with some general information about the data. The dataset has been created by a collaboration of scientists from the University of Genova and the Université de Catalunya. They asked 30 participants to perform 6 activities of daily living while carrying a waist-mounted smartphone with embedded inertial sensors. While performing the activities, the embedded accelerometer and gyroscope stored the data for all 3 axes at a constant rate of 50 Hz. The sensor signals have been preprocessed by reducing the noise and were sampled with a fixed width sliding window of 2.56 seconds and 50% overlap. Furthermore, new features have been aggregated from the sensor time series. Now let's dive into the data. Loading the data, you can see there are about 10,000 sampled data points, with each having an incredible number of more than 500 features generated from just 2 sensors. By grouping the main feature names, we can see there are many different accelerometer, gyroscope, and even gravitational features. Luckily, the sensor data is composed of numerical features. Only the activity column and newly generated data column are strings. Investigating the activities, we can see the 6 activities are lying, standing, sitting, walking, walking upstairs, and walking downstairs. At a rough estimate, all of them have around 1,500 data points. Since the smartphone had a fixed sampling rate and an equal number of staircase up and down walks can be assumed in a scientific environment, we can conclude the participants were about 10% faster walking downwards. Next, we will try to infer these activities using a basic machine learning classifier. Beforehand, we will check if the categories are separable by reducing the dimensionality of the dataset using the t-SNE algorithm and will plot the results. Using a color encoding for the activities, we see the categories seem to be distinguishable in a lower dimension. Furthermore, a color encoding for the participants reveals color clusters as well and implies the separation of unique participants could be possible with this data. Since the clusters differ in their compactness by the activity, we will try to predict the unique user separately for each activity later on. First of all, let's separate the activities. Without tuning the parameters of an LGBM classifier much, predicting the correct activity out of 6 for a smartphone user is possible with an accuracy of up to 95%. Therefore, it is feasible for your smartphone or your apps to know what you are doing while having your phone attached to your body. Let's dive a little deeper and try to distinguish unique users. I'm going to split the dataset by the activity and will train a basic LGBM classifier to predict a unique user for each of them. In doing so, we can spot a unique user out of 30 by their walking style with up to 94% accuracy. Even stationary activities as standing or sitting enable us to choose the correct user with 55% accuracy. It has to be noted, the more motion there is in an activity, the better the prediction. Let's move on and check how long the smartphone had to record data to be this precise. Since every data point depicts a time span of 1.28 seconds, we just add up all points. This reveals a short time span of not even 1.5 minutes for each activity. By adding up the feature importances of the LGBM classifier, we can see both sensors contribute a fair amount to the prediction. Excluding one would probably lower our score significantly. Let's turn towards the staircase experiments. Computing the time each participant needed for these activities, we can see nearly all participants needed more time going upstairs, blue, than going downstairs, orange. Comparing this upstairs-downstairs ratio for all participants shows a wide range in their physical condition. Potentially, this could enable us to infer some insights for the user's health or age. Having no data to underpin this statement, it has to be regarded as speculative. Checking the staircase walking durations for sanity reveals a normal distribution, which should be expected for high-dimensional real-world data. For the next section, I'm assuming the data points have not been shuffled and therefore are in the correct order. Plotting the dimension-reduced data for the walking of each participant could reveal their unique walking patterns. Since these clusters only have a single connection between them, they cannot be the left and right steps, but have to be unique consecutive walking experiments. Comparing the participants by their walking duration, a range of different types appears. Therefore, a fixed walking distance is more likely than a fixed walking duration for this experiment. Plotting the dimension-reduced data for the staircase walking style reveals two clusters for each participant as well. Two distinct staircase experiments can be assumed for the experiment. Now let's try to investigate a single participant. I'm assuming the data points are a time series and have computed the Euclidean norm of the 3 accelerometer axis as a single feature to explore. You can see the original series in red here. Decomposing the series with a singular spectrum analysis reveals the 3 most important components of the walking style of a single user. The main component can be interpreted as trend. The subsequent components are the main frequencies. You can clearly see a frequency change in the middle of the plot. This underpins the assumption of 2 walking experiments, both with a different speed. Splitting both experiments and decomposing them on their own generates better results and displays the walking rhythm nicely. Fitting a sinus curve to the data points now should unveil the step frequency of the participant. By doing so, the first experiment has a slow walking frequency of roughly 1 step per second. Unfortunately, the second experiment has an even lower walking frequency of just 0.5 steps per second. Since the second speed is suspiciously low, there could be a sampling problem and information could have been irrevocably lost while aggregating the dataset. Potentially, the data points are too widespread to reconstruct the underlying frequency in a correct way. This will be compared to a self-experiment in the next section to back up these statements. A dimension-reduced plot of all participants with their walking style reveals 2 more or less separable clusters for each user. Therefore, the above-shown decomposition for both walking experiments should be possible for each participant. Comparing the computed steps per second to a small self-experiment underpins the assumption of having a sampling problem. The slow walking speed with 1 step per second is reasonable. In contrast to this, the second walking speed in the dataset raises some issues. Walking with 0.5 steps per second seems highly unlikely after trying it for myself. Furthermore, a fast walking style has around 1.5 steps per aggregated data point. Therefore, a fast walking style could hardly be extracted with this small amount of data. Since the sinus can be fitted to the data, the correct step frequency can be found within integral multiples of the found frequency. A dataset with raw data or a higher sampling frequency for the points should reveal some more insights regarding the faster walking styles. Summarizing this investigation, within a short time of 1 to 1.5 minutes, the smartphone has enough data to determine what its user is doing, 95% with 6 activities. Who the user is, 94% walking with 30 participants, and even the basics of a person's specific walking style, steps per second. By linking these insights to more personal data of the participants, extensive options open up. In addition, these insights have been extracted from only 2 smartphone sensors, which probably could be accessed by most of our apps. Therefore, let's not consider for how long we've been carrying our gadgets around. I hope this has been interesting for you. Please let me know about your creations. Have a good day.